Okay, so we're going to go ahead and extend the use of trigonometry and those area formulas to finding the area of some polygons. And in this case, I'm going to stick with only regular polygons because if they're not regular, meaning all the sides and angles can be different, then we have no choice but to do the formula over and over and over again on each different triangle in an independent way. And that would be just too long to deal with in this format. It is doable, but it just would take a long time. So we're just going to look at a couple of regular ones just so we can leverage. Now, this is actually what you were asked to do back in your days in math too, where let's say you had a regular octagon. I drew these lines in just so I could make sure that I found the center of my octagon just to make it look nice. And so what I have is a segment that goes from the center of the octagon right here, right to the midpoint of one of those sides. And this thing is called the apothegm. It's not really significant to know that word apothegm, but it is what that's called in math. So what I would do personally is I would just come in here and then I would divide this up so that I could look at one piece. Because if I could study this one piece of that octagon, then I could multiply that one triangle by 16 to find the area of the entire polygon, and I could actually take that side length right there and multiply it by 16 to get the perimeter. So what I'm going to do to start with is I'm going to think about this as 360 degrees coming around here like this way, and I'm going to divide it by 8 because it's an octagon, but I'm also going to divide it by 2, or a total of 16. So 360 degrees divided by 16 is 22.5 degrees. So this little angle right up here in that vertex is 22.5 degrees. So if I did a quick tangent, I could say that the tangent of 22.5 would be the opposite over the adjacent, x over 18. So let's see, that would mean then 18 times the tangent of 22.5 would be, x would be 7.456. Now, again, that would be this length right here. So I'm going to go ahead and store that as alpha A because I'm going to use that a few times. Now, I know already that the perimeter would be 16 times as big as that. So I'm going to hit 16 times alpha A, and I know that my perimeter is 119.29, let's call it inches. Now, as far as the area goes, in this case, the area would be actually pretty nice because it'd be 1/2 the base, which is x, times the height, which is 18. And so this, again, 1/2 times, remember I stored that as A, times 18. This would be the area of that little triangle. But of course, I would need to multiply that by 16 to turn that into the area of the entire figure. And you should not be super duper surprised that we get very large numbers because in area, you're multiplying lots of things together. So it becomes a fairly substantial sized value. That's pretty easy. Now, I'm only going to do a total of 3 examples, but now I have a nonagon right here. There's 9 sides to this figure right here, which means if I were to come in here and divide this up, then 360 divided by 9 would be 40. And so this is a 40-degree angle in the center. But this time, instead of giving you the apothegm, the one that would go from here right to the middle, what if instead I gave you this value right here, which would, let's say, be 8. We'll just go with a nice, easy number. Well, again, because it is a regular polygon, if that's 8, then so is this. And we have side angle side. So the area of this little triangle is 1/2 the product of the 2 sides times the sine of the angle in the middle, which is something we talked about in class. So 0.5 times 8 times 8 times the sine of 40. And we're looking at the area of that triangle being 20.569. But of course, then that would mean the area of the polygon would be this number multiplied by 9 because it would take 9 such polygons to make this up. So the area of this one would be 185. 1, 2, 2, 3. Now this one's obviously much, much smaller because its value is 8 versus 18. So a considerably smaller polygon, although it didn't look smaller. The last one is, I think, a little bit more interesting. It's when you try to find the area enclosed between maybe a circle and a polygon. And so in this case, I picked, let's go ahead and count this up. Let's see, what do we have here? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a 12-sided figure. So let's imagine, if we will, again, now I could do like I did on that last problem and give you the apothem and go to the middle, but this time I'm just going to keep things really nice and easy. And let's say this is maybe 10. I want to find the area between the circle and this polygon, which is known as a dodecagon. So we're going to start with the area of the circle, and we're going to subtract the area of the polygon. So the circle is no big deal. It's pi r squared, right? So that's going to be easy. That's just 100 pi. That didn't take much. And then what we need to do is go find the area of that polygon. So since it's a dodecagon, there's going to be 12 triangles that make this thing up. And so we have 1/2 of 10 times 10. That's the side times the side times the sine of the angle in the middle. And that angle in the middle would be 360 divided by 12, which is 30. Sine of 30. Now, what may surprise you is when you come over here and you start typing that in, we got a really nice, easy answer. I guess I missed a button there. And I got 300. Just dead even 300. That's a little surprising. It was a perfect number, and the reason why is because the sine of 30, this is a 30, 60, 90 triangle, and the sine of 30 degrees, also known as pi over 6, is 1/2. So that was actually kind of nice. So this would be the answer of that area in the middle. And you're going to notice that 100 pi, let's kill that, sorry about that. 100 pi minus 300 is actually not a very large number, but of course we didn't have much area left over in the middle of those two things. And the more sides that you would have in that polygon, the less value that you would have in there. And so as it turns out, if you did 1/2 the product of the two sides times the sine of the angle in the middle, and you did the limit as theta goes to 0, meaning that you make this thing smaller and smaller and smaller and smaller and smaller, you're going to get pi times that radius squared. So as it gets more and more sides, you're going to get closer and closer to that circular case. And in fact, that's where pi r squared comes from. But that's something that you'll learn about in calculus next year. So that's a little thing about using polygons and triangles together to find area. All right, I'll see you back in class. Bye-bye.